Hi everyone, today I'm going to share with you how you can draw the nucleophilic addition mechanism. Alright, so there are a couple of key points in this lesson. Alright, so the first thing that we have to do is to identify the delta positive carbon. So what do I mean by delta positive carbon? Right, so take a look at this carbonyl compound here. Alright, I think you should be able to tell that the oxygen atom is more electronegative. Alright, so you pull the electrons towards itself. Okay, so this gives this carbon a delta positive charge. Right, the carbon that's connected directly to the oxygen. So you'll get a delta minus here and a delta minus here. Right, so this is the first step to identify the delta positive carbon. And in this very special example, alright, we have to see which is the more electrophilic side. Right, so this mechanism is called nucleophilic addition. So the group that is attacking is our nucleophile. And so this other group is my electrophile. So you want to see which of these sides is the most electrophilic. So let's say I only have 1 mole of this reactant and 1 mole of this reactant. So I should at the end only either add to the one on the left or at the one on the right. Right, so how do I decide? I have to see which has a stronger delta plus. So if I take a look at the groups that are connected to the delta plus carbon, you can see that the one on the left, also a ketone, has 2 electron donating groups. So it diminishes this delta positive charge to a larger extent than the one in the aldehyde, because the aldehyde only has 1 electron donating group that gives electrons to it. Alright, so that's why from this example, I can identify that what I'm interested in is this aldehyde over here. Right, so that's the first step to identify the delta positive carbon. So in the second step, we have to push the electrons from the nucleophile, alright, to the delta positive carbon. And so in this case, alright, our electrons come from, we need a little bit of Cn minus, alright, to kickstart this reaction. And notice the negative charge is on this carbon atom because the carbon atom is going to be connected to this position here. So how should I draw the arrows? Alright, I always start from the electron source to the electron sink. Alright, and then now this carbon has, inclusive of this hydrogen, you have 5 bonds. So it cannot have 5 bonds, so it has to push one other bond up and it should end up on the O atom. So the negative charge ends up on the oxygen atom. Alright, so what you will have at the end of the day is this. Alright, with a Cn group here. Okay, so this is where this special part of the mechanism comes in. Your here is Cn. Alright, we'll come to the rescue. Okay, because it has a proton that can be donated to this O minus atom. Alright, so this is the slow step, this is the fast step. I will end up with this product, alright, which is a cyanohydrin. Alright, cyanohydrin. Okay, so the thing that we have to look at this point in time is, why do we need this proton here? Right, so assuming we don't have this proton here, what is going to happen is this pair of electrons, okay, is going to come back here and kick this Cn out. So altogether at the end, we are going to get this product. Alright, so if this step occurs, we are going back to square one. So that is why it's very important for you to have HCN present. So if you contrast this to your nucleophilic substitution mechanism, which uses purely Cn minus, right, you should be able to see why there's a need for this HCN. So this is the nucleophilic addition mechanism.